Welcome back to Math 135. Today we're looking at Lesson 15, Graphing Polynomials. Now you might wonder, what in the world is a polynomial? I've got a lovely explanation for you here. It actually looks kind of frightening, but it shouldn't be too frightening. All of these A's have subscripts just to indicate that they're different from each other, or they might be different from each other. And all of these A values are your coefficients, you know, like 3 or -2 or 1/5. They just have to be real numbers. And n, that's the exponents. The n is going to be any integer. So it might start out with n is 5, or n is 3, or n is 19. And, by the way, some of the coefficients could be 0, okay? That's an idea of what our polynomials might look like. And here is one such polynomial. And what we want to do is kind of explore on these first few what their graphs look like so that we can learn how to do graphs of these without making horrendously big tables of value. Now, I do want you to fill this graph in. I'm going to go on into the next slide in a moment and show you the graph. And if you'd like, you can fill in some of the values here. I'll help you get them. And what we want to do is we want to focus on end behavior. Now, if you've never heard of end behavior, it really means not looking in where we usually look at functions. You know, usually you're looking -10 to 10. No, we want to look at the big picture. It's like you were out on the moon and you're looking back at it. All you see is the really big stuff. You don't see the small details in it, okay? So for this particular cubic equation, when we look at the end behavior, this is the graph that we see. So you might want to put some of these values in your table, and yes, these are incremented by millions, okay? So at -150, we're at about -3,300,000, something like that. And so you're going to want to plot something close to that on your graph just so that you can have an idea. -150, comma, -3,300,000. And this one, I'm sure he's not exactly at this place, but he's pretty close to -100, comma, -1 million. And it looks like we go right through the origin. And then we have 100, comma, 1 million. And we've got 150, and he's at about the +3,300,000. I'll let you put that on. Now, the question is, you know, why is it looking this way? Because when we looked at some basic graphs back in an earlier lesson, you saw that anytime you had a cubic, his graph basically looked like this. So you say, well, why did this guy basically just look like a cubic? Well, here's why. When we're talking about extremely large numbers, and we put them into this equation, and you might even try some just to convince yourself. If I take something like 1,000 and I cube it, think of how huge that becomes. And if I have 1,000 and I just square him, it's just not nearly as big. It doesn't have nearly as many zeros. And so, even though I've got that way negative number and I'm going to add, I don't add hardly anything. You know, it kind of reminds me, because it's all relative here in size. Let's say you're waiting tables in some very swanky restaurant. And I go in and I just think you have an amazing talent at what you do. And so I decide to drop you $1,000 tip. Your lucky day. Now, do you think that on a college instructor's salary, my checking account might notice $1,000 gone? Yeah, I don't have a whole lot of zeros in there. Okay. Now, the very same day, Bill Gates walks into your restaurant, and he likes you as well. He drops $1,000 tip. Do you think Bill's checking account is going to miss that 1,000 much? Yeah, do you realize that it's all about relative size? And relatively, in my case, it would be noticeable, but in his case, it would not be noticeable. All right? And that's why, in the very big picture here, this guy looks basically just like y equals x cubed. Okay. So now what we want to do is we want to focus in on some details as well, because there's two things you're going to need to find. You're going to need to find the end behavior, the big picture, and you're going to have to be able to find some of the details as we do look in closer. Things like x and y intercepts, especially x-intercepts. And these guys have another name as well. An x-intercept is also called a root. I don't know who dreamed that up, but oh well, we'll use it. Okay? So we want to find out where these roots are happening and how many turning points we might have. Now again, I've given you a table of values if you want to fill that in, and I've given you a graph if you've pulled this all down from Blackboard. And here is a really nice close-in picture. Now by the way, this is the exact same function that we looked at a few minutes ago. That looked like that. And then you look at this and it's like, that's not even the same thing. Yes, it is. We're zoomed in a lot closer and we're able to see detail. See, it crosses the x-axis at -2. It crosses the x-axis at -1, so those are both roots, and it crosses at 1. And what I'd like to do is take that equation, x cubed plus 2x squared minus x minus 2, and let's find those x-intercepts. Now, I know, we know what they are, but how would we algebraically find those x-intercepts? You know, we've worked on these in the past. You see 4 terms, so you decide you're going to group it in pairs. I can factor an x squared out here. I can factor a -1 out, and the nice thing is that's going to give me the same factor inside of parentheses. And then I have x plus 2 times x squared minus 1, and I have x plus 2, x minus 1, x plus 1. And that's why your roots are sitting at -2, 1, and, oh, I made a mistake here. This is a +1, -1. Okay? And that's exactly what I see right here. And is that what I would expect out of a cubic equation? Yes. Now, we do use the term turning points. The idea being that if I have got two distinct meaning different from each other, roots, well then I had to go up and then I had to come back down. That means that in between there I had to turn around. So if I have 3 roots, it makes sense that I would have 2 turning points because the curve had to turn. These are nice continuous equations. I can put any number in for x. Its domain is the entire real number set. Okay. By the way, we've got a y-intercept of -2, which is very easy to find by putting your 0 in. Okay, so we've got detail. Now, by the way, one last thing before we leave this. Even though we don't see quite the same behavior, you do see an indication of end behavior. And here's what I mean. You know that you're going to drop off. And you know that because the end behavior dropped off. See, in this case, we didn't see the 3 roots just because the details weren't being shown to us, but we knew that it was going to drop off after a certain point. And we know it's going to shoot skyward after a certain point. And what's very interesting about this is I know I have the whole picture because a 3rd degree equation could have at most 3 roots, that is its end behavior, and so that's the entire story. Okay? Well, continuing on. What had the most impact on the end behavior? It's the degree of the polynomial, the fact that that was a cubic, and you know that that's what a third degree equation is going to look like, and the leading coefficient. Now you might say, why does the leading coefficient matter? Remember that leading coefficient would be your A value in a transformation. It would be a vertical stretch, and if it's negative, it flips it over the x-axis. So we'll have to watch for that. What had the most impact on the location and the behavior of the roots? Well, we found our roots. We found our roots by factoring that particular polynomial. Okay? Now, I've used a term here in my PowerPoint called multiplicity. I said the factors of the polynomial and the multiplicity of each factor affects the shape. Well, the multiplicity is the exponent on that particular factor. In this case, each of these had a multiplicity of 1. Now, you'll see other multiplicities in later examples, and what that basically meant was that we went right on through the axis each time. And we'll add to this information as we go. Okay, we're going to do the same thing that we just did. We're going to look at end behavior, then we're going to look at details, but I've changed the function. Now, I want you to notice that he's a fourth degree. He's a fourth degree, a quartic. Now, that means that he can have up to 4 roots or x-intercepts. Okay? What does that mean for his end behavior? What's the big picture going to look like? If you put in humongously big numbers and you run them to the 4th power and then times a negative, what will it look like? Meh. Hey, and by the way, when we talked about power functions, I told you that all of the evens, because this guy is one of your even exponents, a 4th degree, and I said they all kind of look like parabolas, except if it's a 4th degree, it's going to kind of sit in a little bit more, and you can actually see some nice evidence of that. If you want some help in making your graph, looks like we go through the origin. We've got negative 100, and I had to change my values here, because running that to the 4th power just got huge. I think, yeah, that's going by 100 millions. That's negative 100, comma, negative 100 million. And at negative 150, we are almost at negative 500 million. It's huge. And you know what's really kind of funny about that is, think for just a second, what's the domain of this function? It's all reals. Do you think I've even begun to look at all reals when I'm at negative 150? Oh, heaven forbid, it's going way far out there. And what's this going to do? It's just going to continue to drop like crazy. Hey, if you take a look at this, do you realize that it totally looks like I have symmetry? And would you expect symmetry with the y-axis on an x to the 4th? Yeah. Remember, you'd have y-axis symmetry with this guy. You'd have symmetry with the origin with that guy. Okay. So we've got a rough idea of this outside the end behavior. We know that he's going to make this big arch opening downward, and he's going to be heading way down on both ends of this graph. So then what we want to do is look in and see some of the details. Now remember, we're looking for potentially 4 roots. Well, let's see if we can find out where those roots are before we get started. Now remember, roots are the same thing as x-intercepts, and if I'm looking for an x-intercept, I always put 0 in for y. So that's equal to 0. Now when you look at that, it's a little bit scary because it's a 4th degree, but you realize, oh, I have the greatest common factor of x squared. Now since this leading guy's negative, I'm going to factor out a negative x squared. And that would leave me with x squared minus 2x minus 8. Oh, and now you know we're home free because we've talked about this. While, yes, all quartics are solvable, they're not necessarily easily solvable, but this guy is, because here's a quadratic. So we have negative x squared, we have x minus 4, we have x plus 2. So we have got roots at 0 from here, at x equals 4, and at x equal negative 2. Now, you know, this is very interesting because you look at that and you say, wait a minute, Mrs. Blanton, you only have 3 roots. Do you know what happened to the 4th one? Why are there only 3? If I solve this guy, I would have x squared equals 0. And then when I square root, there's a positive 0 and a negative 0. Do you realize that this guy really counts as 2? He's considered a double root. So I do have 4 roots. He counts as 2, 3, and 4. Now let's look back at that word multiplicity. This root has a multiplicity of 2, and each of these roots has a multiplicity of 1. Now let's see what that did to the graph. Okay? As we look at the graph, now remember, this is the details as we look in closely. You see the root at negative 2, you see the root at 4, and look at 0. Isn't that interesting? You did hit the axis. You did actually hit the point 0, 0, but you didn't go through the axis. What happens is that you hit that axis, and what we like to say a lot of times is that you bounced off of it instead of going through it. What made it bounce? Well, since the other guys didn't and this guy did, it must have something to do with the square. And you know, doesn't that kind of make you think of the parabola? The idea of it bouncing at that vertex point? Well, the reason why, by the way, it does bounce there is if I am a little bit to the left of 0 and I plug it in, I get a positive value. If I'm a little bit to the right of 0, I plug it in, square it, I get a positive value. It's because of the squaring that it doesn't allow it to change signs. Well, isn't that interesting? Okay, so anytime I have an even multiplicity, it's going to force my graph to bounce. Isn't that neat? So 1, 2, 3, 4 roots. I see all of my roots, and I know that my end behavior is, boom, drop like a rock on both sides, and there we go. So I know what's really very interesting about this is all this knowledge is actually very important even if you're going to grab that graphing technology. You know, I love the graphing calculators and I love using WinPlot, but how do you know you have a full graph? Maybe there's some action going on and you just aren't looking in the right window. If you understand your polynomials, you'll know I've got it all. And I know I have it all because I've got 4 roots accounted for. 4 roots, and I have 1, 2, 3 turning points. 1 less turning point than you have roots. And so everything's accounted for. There is nothing else going on this graph except dropping off. Okay, that's powerful knowledge. And so now what we want to do is start looking at these guys on our own. And I said we want to determine the zeros. Oh, that's very, very important for us. And we want the multiplicity of each zero, because that will tell us whether it goes through the axis or whether it bounces. Okay? Determining the y-intercept is a good idea. Make a rough, and notice I even bolded that and put it in italics, rough sketch. I did not even put a y scale on here because I'm not really concerned with how far up and how far down it goes. I simply want to know the main idea of what's happening here. Okay, so let's start analyzing this guy. The best thing to do is, let's see if we can factor this. A lot of times they're already given to you in factored form, but if not, you will have to factor. So it's x squared plus 4x plus 4. You know, I took the greatest common factor out, and now this guy will nicely factor, and I have x times x plus 2 times x plus 2. Right? And you know, if you want, you could even say that this is x times x plus 2 quantity squared. Okay, so having that guy in factored form is really nice because it makes it extremely easy for me to find the zeros. Remember, you always put 0 in for the y. Well, if you have him factored, you're looking at the x-intercepts or the roots because you take this factored form, set it equal to 0, all the work's done. X is 0 or x is negative 2. And this guy has a multiplicity of 2. And this one has a multiplicity of 1. All right? So I come to my graph and I say, all right, I know at negative 2, I've got a double root, or I've got a multiplicity of 2. Now, that means either he's doing this or he's doing this. He's going to bounce. I'm just not sure yet from which way he's coming. Okay? And then at 0, I go through the axis. Now again, I don't know if I'm coming down through the axis or if I'm going up through the axis, which means that I really need to pull some other information. And that other information is, what is my end behavior? Now remember, what's the biggest impact on the end behavior? It's this first term. That guy has got more power than any other term, so he's really determining the overall shape of the graph. So with a third degree and a positive 1, it means that my end behavior looks like this. Yeah? So it means that I'm coming from below. Now, at negative 2, that's that multiplicity of 2, so I have to bounce. So it comes up and bounces. Now, I don't know how far down it bounces, but that doesn't matter. I know it bounces below, and then I have to turn and go up. And have I missed anything? It's a third degree, so it has 3 roots. Here's 2, 3. I've got 2 turning points. I know what the end behavior is doing. That's a good graph. Now, is it 100% accurate? No, but I know a lot about what I should expect. And if I now put it on WinPlot or I put it on my favorite graphing calculator, that's the kind of picture that I should see. Okay. This one's really nice because it's already factored for me. So boom, I am ready to go. Now, I like to think about, I guess it doesn't matter which one first, but I like to think about end behavior. This negative 1/2 is your A value. It's going to be your vertical stretch compression factor. It's not a variable. It's not giving you a root. So from here, I've got 2. If you multiply that out, you have an x squared, then times an x to the first and an x to the first. This is actually a 4th degree polynomial. Now that means that his end behavior is either this guy or it's this guy, because that's what an even degree is going to look like. And then I go to this and I say, oh, the fact that he's negative, this is what I've got. This is my end behavior. All right. Now let's put the roots on. I've got a root at -3, and he has a multiplicity of 2. Now that means he's going to bounce. He's either going to bounce from below back down or from above back up. I have a root at 2, and it's a single root. It has a multiplicity of 1, and the same thing at 5. Okay? With this idea, you know I need to be coming in from down below on the left. So I always start on the far left. This is my farthest to the left point. So I come up, I'm going to hit that and drop. Then I'm going to be coming over, I don't know how far I drop, but I have to go back up through at 2 because 2 has a multiplicity of 1, so I just go right through that axis. And then I'm going to turn and boom, go back down. That's pretty slick. That's a good, reasonable graph for this particular 4th degree quartic equation. Hey, one last thing that we might want to take a look at is, if it's not too bad, we'll try it. How about a y-intercept on that? And the reason is, I'm willing to put money on that it's going to be a negative value. But let's just verify that. If I put a negative value, if I put a 0 in there, g of 0, I would have -1/2 times 9. You know where I got the 9? 3, then square it. And then times a -2, and then times a -5. Well, those will nicely cancel, and I get -45. So yeah, I actually do know the y-coordinate there. It hit at 0, -45. But I don't have a scale on, so I don't really care. Okay? That's pretty quick to be able to do all that work. Now, how about this guy? We've got an x cubed, an x squared, oh my gosh, an x to the 4th. So let's see here. What's our overall degree? 3, 4, 5, 6, and another 4. Oh my goodness. This guy is a 10th degree. Now you saw that I had to put that 4th degree on scale with increment of 100 million. Can you imagine with a 10th degree? This thing's going to go nuts in no time. Now since that's even, it means that either I'm this U-shape up or U-shape down. Now with a 10th degree, he's really going to be somewhat flattened out. They're never completely flattened out, but you know, somewhat scrunched there. I look then at the A value and I see that it's a +1. So that means that it's going to be this guy. It's going to be opening upward. All right. Now let's get our roots on there. I have a root at 0 because this guy is 0 when x is 0. And he has a multiplicity of 3 for x equals 0. X equals 5, coming from this factor, has a multiplicity of 1. X equals -1 has a multiplicity of 2. Boy, this could get tricky. In fact, this would be just a nightmare to put on your calculator because I think it's going to be going so nuts. And then x equals 7 has a multiplicity of 4. Okay, so here are my roots. Now I know that I have those particular roots, and we'll talk about how these multiplicities are going to work in there. But I know this is my end behavior, so this is going to get me started. From the left, the first root I run into is this -1. Now that means I'm going to be dropping into him, so I drop. Now, at -1, I have a multiplicity of 2. So with an even, it means I have to bounce. Now I'm not going to bounce real far because I have to come right back here. So I'm going to just bounce a little, come up. And now I've got to hit this root at 0. And he has a multiplicity of 3. Now here's what you do need to realize. On all of my odd multiplicities, if they're odd, they're going to go straight down through or straight up through if the multiplicity is 1. If it's any other odd, it looks like this. Looks just like that cubic. It's going to go up through, but it's going to kind of pause as it goes. Make an S-curve kind of shape. Okay, now that's not a big deal for us, but it means that as I go through here, I want to try to make a little bit of an S-curve. Now I know I'm going to have to turn pretty quickly to hit that 1. Now at x equals up, I wrote a 1. I put a 1 in there, and I really meant a 5, didn't I? Let's see, I have a root at -1. I have a root at 0. I have a root at 5 with a multiplicity of 1. Now with a multiplicity of 1, I just go boom, up through there. Now how far did I have to drop? I don't know, I don't care. And the last thing is I've got a root at 7 and he has a multiplicity of 4. Now because that's even, he's got to bounce. So boom, and up I go. That is one weird looking graph. Now by the way, I didn't mean to violate the vertical line test there because I wouldn't want to do that. These are functions and they will pass the vertical line test. But the idea is the end behavior is this upward curve. So if you look at the big picture, it's this upward curve. But then as you look in on the detail, well, at -1, I have a root, but it bounces. At 0, 0, I have a root, and he kind of S-curves through. At 5, we have a root, he goes right on through it. And then at 7, he bounces and goes on. Okay? So it's extremely cool stuff that we get to do there. Now, to recap what we figured out here, because this is really powerful stuff. It's an extremely easy process as long as you can get these guys factored. And you can get a good handle on graphing polynomials of surprisingly high degrees. I suggest you determine the overall degree of your polynomial. Now, if it's all written out nice and neat, like the beginning polynomials, it's obvious. If it's written in factored form, then you have to think about if I multiplied this all out, what would this degree be? Now use that degree and your leading coefficient to determine the end behavior. And of course, the only thing that leading coefficient is really going to add to the story is whether you're opening upward or downward for the evens, or whether you're going in this direction, or if you're going in this direction in the case of the odd degrees. And then you'll look at your factors. You may have to factor it, or it might already be factored for you, because those factors are going to give you your roots. And your roots are the same thing as your x-intercepts. And you want to first look to see where you have roots, and then you want to look at their multiplicity. If you have an odd multiplicity, the curve will go through the axis. And if you have an even multiplicity, the curve will bounce. So these are really kind of fun. Now I suggest that as you go ahead and graph these, use all of your analysis, come up with what you think to be the answer. Then you might pull up WinPlot or grab your graphing calculator and put these equations into your technology and let that technology graph it. Now, the one thing you're going to have to be careful about is you're going to have to set some really large range values for these high degree polynomials to be able to graph, okay? But it would give you a chance to kind of double check yourself. But don't get too scared, because when you first graph that, if you don't have a good window, it's going to look just totally crazy. So have fun with this assignment, and I'll see you in the next lesson.